Wonderful. Can everyone hear me okay? Awesome. Thank you so much, Stuart, for the kind introduction. It's been a real pleasure to be here so far today and get to meet all of you great people. Definitely for my first time at McMaster, and I respect a lot of the work that comes out of here. I'm continuing to grow my knowledge of the Great White North and get more aligned with the Canadian higher education system, especially in chemistry, chemical engineering. So I'm really honored to be here and really appreciate the invitation. I really hope I can share today some perspective of the work I've done on reactor design strategies for electrochemical systems. Really at the heart of the work I do is reactor engineering, very intertwined in chemical engineering, but applied to electrochemical systems. So hopefully you will see some of that today, and I can give you some insight on some of my past work and the work that my lab is going to pursue in the next several years at the University of Toronto. So in the spirit of the Great White North, just a little bit about me. So in some ways, my academic journey has always been leading me gradually northward to the University of Toronto. So I'm from Ohio. I'm from the States originally. I went and did my undergraduate at Ohio University, where I had the privilege and the opportunity to do some really great undergraduate work in electrochemical systems. So that's where I first got introduced to the idea, kind of on a whim. I got lucky to join a group doing some work on ammonia electrolysis, and that really catalyzed my career in working on these types of technologies. I went a little further north to MIT to do my doctorate. I'm going to talk about a lot of my talk today. We'll talk about work I did there with Vic Brushett on redox flow batteries. I spent a postdoc at the University of Michigan, moving maybe just a little bit south, but still staying pretty far north. I'll talk about some of that work today as well. And that eventually led me to the University of Toronto. So in addition to electrochemistry being a kind of unifying theme of all the places I've been on my way northward, another unifying theme is that I seem to follow around places with beavers as mascots. So coming to Canada with a beaver as the national animal really felt fitting along this trajectory, as well as the beaver being the mascot for the Varsity Blues. And as well, the beaver is nature's engineer, so that is why it's MIT's mascot as well. And then Beaver Creek, of course, no other mascot would really make sense for a town with that name. All right, so that's just a little bit about me, just give you some perspective on kind of where I've been and where the talks or where the research I'm doing takes place. But again, that unifying theme is electrochemistry. And so just to give you a little bit of perspective on kind of my vision for this area, my kind of vision around sustainability in this space really goes back to thinking about, again, chemical manufacturing and chemical industry. So I'm kind of skipping over the introduction on the importance of reducing CO2 emissions, industrial decarbonization, and really kind of jumping right into where I see kind of where we are in the energy transition, right? And traditionally, maybe not everywhere in Canada where there already is a lot of renewable electricity, but kind of the general picture of our energy system worldwide is most of our energy comes from oil, natural gas, coal, burning these things to generate energy, generate process heat, to generate electricity. And so we generate all that energy, it moves, that we use that energy to make chemicals and do all sorts of things in manufacturing. We need a lot of energy. But we also use that oil, natural gas, all these great carbon products in those same types of chemical manufacturing processes. So this is really generally driven by fossil fuels, carbon we pull out of the ground. And we're, of course, in the middle of this energy transition where I think electrochemistry and electrochemical technologies has a pivotal and really meaningful role, right? So we're beginning this global transition looking towards renewable electricity, of course, incorporating things like wind and solar. That's going to change how we incorporate energy into processes, how we incorporate energy into the grid. Of course, on one hand, when it comes to electrochemical systems, that means the incorporation of energy storage systems. So in addition to our kind of pumped hydro that we kind of have classically as an energy storage system today, we're seeing a large growth and boom in the development of battery technologies, of which electrochemical technologies play a core role. And looking towards the future, kind of the motivation for my work and where this comes in is thinking about how we are then transitioning our chemical manufacturing paradigm, moving away from some of our thermochemical processes where we can use renewable systems or more sustainable systems like electrochemistry, as well as incorporating things like biochemical systems, photochemical systems, more electricity-driven separations or membrane-driven separations, kind of changing this chemical manufacturing paradigm where we can still use a lot of these great carbon sources we have, but in my opinion, we're not wasting that carbon so much by burning it. We're focusing its use on more conventional chemical manufacturing and kind of more end use of that carbon. But in addition to that, I think this kind of paradigm also opens up a wide range of more space and sustainability, where moving beyond these carbon sources, reusing and making more use of the carbon sources we have readily available. So that is transitioning to things like biomass, reusing the plastics we've already used that the oil and gas to make, then capturing carbon from the atmosphere, recovering things like metals and materials from electronics, the batteries we're using again, and all of these things. So I see this as kind of a pivotal transition to incorporating renewable electricity, making our kind of chemical infrastructure more sustainable. And I think electrochemical technologies will kind of be core in this transition, especially in their ability to enable sustainable, versatile, and modular chemical manufacturing and chemical technologies. And so this is really the vision that unifies a lot of my research and is kind of the core driving force behind what I aim for my group to continue doing at the University of Toronto. So what my group aims to work on and what themes you're going to see in my talk today really revolve around this idea of reactor engineering and thinking about how we go from kind of fundamental principles, things we're measuring at the batch scale. What kind of questions do we need to ask of our chemical systems, of our electrochemical systems, to understand how we transition from something we see in the lab to something that might undergo continuous operation, think a la a plug flow reactor, and move up to something that looks like a practical embodiment. So what questions do we need to ask and how do we scale those systems? And we apply a range of approaches looking not only at the kind of beaker scale, looking at very fundamental electroanalysis, characterizing those redox processes, up through characterizing and designing and prototyping reactors to test those reactions, and then using things like mathematical modeling to translate what we know and what we find at that scale to understand how something might scale in a more practical application. This is really at a core of what my research focuses on, and you will see elements of each of these in my talk today as I kind of talk about some of my past work. So going back to our kind of big picture, again, I think there are a lot of places electrochemical technologies touch and a lot of impacts they're going to have. I'm going to talk about two facets of this paradigm today. I'm going to talk about electrochemical energy storage in the form of redox flow batteries, sharing some of the work, or a lot of the work I did during my PhD on that topic. And then I'll transition to talk about my postdoctoral work in polymer recycling at the University of Michigan, and kind of which will extend to some of the work we're doing today. So to kick us off, I think I first want to introduce kind of what a redox flow battery is, how it differs from a kind of conventional system, and why they're useful specifically for grid scale energy storage. So this is an emerging technology that's being installed more in modern renewable installations and continuing to see a lot of growth in the energy industry. So hopefully we're all familiar with the kind of idea of a conventional battery, right? We have them in our laptops, we have them probably in our pockets and our cell phones, so mostly hopefully familiar with like a lithium-ion battery, for instance. And how a lithium-ion battery operates is by storing energy in solid materials that exist in something like an electrochemical cell, where we intercalate and deintercalate lithium, and that allows us to store energy effectively in the solid state by storing lithium and energy in the form of that lithium in these materials. But there's a limitation in thinking about how this scales. Right? If we want something that operates with more power, converts energy faster, we need to make this battery bigger. Similarly, if we want something that stores more energy, we also need to make these electrodes bigger. We need to make the entire battery unit bigger. And what that effectively does is it constrains our energy and power ratio based on the design of that battery. And so what that means is if we were to scale this for something like the grid, so moving beyond what's in our phone, and thinking about the megawatts that exist on a grid installation, we're talking about just making a bunch of batteries, or making these batteries a little bit bigger and then incorporating a bunch of them. What that says is that our energy and power are coupled in the form of scaling. That has implications in costs that I'm going to talk about in a minute. So if we transition, instead of storing energy in solid materials, if we instead store that energy in liquid electrolytes, then we can take those liquid electrolytes that are carrying some charge storing species and pump those electrolytes through our reactor, the reactor effectively being our battery, and we're storing energy in these liquid solutions. Then what we have effectively done is we've decoupled energy and power. So our energy is based on how much volume we have of our energy storing material. Our power is based on how big we make our reactor. And so by decoupling those things, this allows us to scale the system better. Additionally, we've made this an open system now. So our manufacturing, our maintenance is a little more straightforward. We've already made the system open. So opening the system up, replacing components, replacing electrolytes becomes a little more straightforward. Whereas with closed form batteries, you typically have to replace the entire unit or recycle the entire battery. But of course, this is a bit of a new technology. We don't see it everywhere, and that's because current embodiments are relatively expensive for a variety of reasons. But looking at the cost of these systems, they're relatively on par with what we see, and this is unit agnostic a little bit, but there's more to show trends that what I mentioned with lithium-ion batteries not really scaling all that well. You see this red line where no matter how much our scale is, so this is characterized by our discharge duration, so something like your energy storage capacity of your phone might be on the order of hours. Here we're looking towards days and weeks and months, where as we go to increasing scales, really our lithium-ion battery doesn't really improve in scale, but flow batteries change over the course of this, over the course of our discharge duration as we transition from the capital components of the reactor to just the raw energy storage cost of our materials. So there is an incentive to going to these larger scales or these grid scales when it comes to redox flow batteries. But still, we're only on par. And we want to try and find what our future embodiments are that we can continue to drive down that cost. And if we grossly oversimplify this figure of dollars per kilowatt hour, our cost per energy stored, then this is really a function of the cost of our materials, like I mentioned, as well as performance metrics around the battery. So our energy density, our efficiency, and our lifetime of those materials. So figuring out how we make these systems more efficient, how we make them operate better, is going to have direct implications in terms of improving this cost picture and helping us find what future flow battery technologies, what future materials that might make up a system, how that's going to improve our overall picture and make these systems more competitive with our much more mature lithium-ion technology. So to understand how we make these systems better, I think it makes sense to talk a little bit about what makes up a flow battery, what it consists of. So like I said, we have our liquid storing electrolytes. So these are charged storage materials. These can be inorganic species that access multiple oxidation states. So here we're storing electrons by changing the oxidation state of these materials. These can be inorganic. They can also be organic species where we can add and remove electrons from these species to store energy. And these species are dissolved in a solvent. That can be water. That could be something organic. And they have some supporting salt, so some additional ion species that help us conduct charge and make these electrolytes conductive. Then we have some reactor. This is typically a parallel plate reactor or a plate and frame reactor where we have various components. This is kind of where all the reactions take place. So in here we have some positive species that goes to A+ and releases an electron upon charging. And then that electron goes over to our negative electrode where it reduces some B+ to a species B. So we have our negative electrolyte over here, positive electrolyte over here. And these reactions go back and forth depending on when we're charging or discharging. These reactions in our reactor take place at some porous carbon electrodes. Typically, these are something with high surface area that allow for high mass transport rates and fast kinetics for our reacting materials. These can be carbon cloths, carbon felts, and carbon papers, essentially interwoven bundles of carbon fibers that give us high surface area and are conductive for doing electrochemical reactions. And then lastly, the cell is separated by some sort of ion exchange membrane. So something that allows our supporting salt ion, these little yellow dots, allow those to pass freely through the membrane, but keeps each of our species on its respective side. If those go from one side to the other, they are essentially lost, and we lose the energy storage capacity of those species. So we want something that is selective and keeps those on their respective sides of the cell. Now, like any good chemical system, there are complex property trade-offs that kind of frustrate our ability to find really an optimum set of conditions or an optimum set of materials, where if we look at each of these components we've talked about, just to highlight a few examples, for our energy storage species, so our, in this case, redox active organics, we want something that gives us high voltage and high solubility. But to get high voltage, you need large energy differences between these two molecules. And as we go into more energetically unfavorable states, where we get these high voltages, we compromise stability, as again, these are not favorable conditions for molecules. So we often have to balance high energy with high stability. Likewise, for our electrodes, we want something that has high surface area for electrochemical reactions. But if we go too high surface area, we restrict porosity, and we're pumping electrolyte through these electrodes. So we induce a lot of pressure drop, and then we have to pay an energy penalty to actually pump electrolytes through these materials. So we need to strike a balance between hydraulic resistance and surface area. And for our membranes, we have a classic permeability selectivity problem where we want high ionic conductivity of our supporting species, but we also need to limit our active species permeability, as we don't want to lose energy, and that's going to compromise our long-term stability of the system. So with all of these complex property trade-offs, a lot of my work to date has really focused on navigating the relationship between these properties and their performance metrics. So how they cycle, how long the system performs, how long it will be stable and maintain its energy and capacity characteristics, and understanding the relationship between these two such that we can both predict performance from material properties, but also identify a set of performance conditions that we want to achieve and find materials or find characteristics of a system that satisfy that set of performance criteria. So to answer this question, my kind of PhD work really looked at both theoretical and experimental characteristics, both designing new experimental techniques and leveraging mathematical models to understand these trade-offs and predict performance for more broader mathematical optimization strategies. So I did some work that I'm not going to talk about, developing sensors to be able to characterize and understand the evolution of these electrolytes over time, looking at the time-dependent performance of our electrolyte materials and how those evolve over time, being able to track their concentrations as the battery is being cycled. I did a bulk of my work in this area of mathematical modeling, trying to understand performance trade-offs for different materials. I'll talk quite a bit about that today and how we use that information to understand how to scale up the system. And I also developed experimental techniques for characterizing membranes. So trying to understand how those membranes behave under electrochemical conditions and how we can functionally characterize the properties in a real system or in a practical embodiment. So to start thinking about how we build a mathematical model around this, how we try to understand these relationships between performance and material properties, let's just talk generally about how a flow battery operates. So I like to think of these as kind of miniature chemical processes. They behave with a lot of the mass balance characteristics we're used to seeing in a reactor, only applied in an electrochemical context. So we have two sides of our cell operating in tandem, where we're shuttling electrons back and forth. And we have two redox reactions, right? I shared these earlier. B goes to B plus, or sorry, B plus goes to B when the system's charged. At the same time, A goes to A plus. And we apply some current to the system. So current in this case is just something like coulombs per second. If we fix the current, we're fixing the supply of electrons, essentially applying a constant reaction rate to the system at any given applied current. So if we charge our system, we go from A and B plus to A plus and B, and think about our concentrations of each of these species. Generally speaking, these concentration changes are linear, with the slope of that change being just proportional to the current. Again, this is what you would expect in a mass balance for a constant reaction rate. So you get this linear change over time. And then we discharge the system back. We apply a current in the opposite direction to extract energy out of our battery. And our concentrations reverse course and go back essentially to our starting state. And so when we cycle a battery, we repeat this process over and over again as we charge and discharge, put in energy, and take out energy. And when we're applying a current, typically we're measuring a voltage. So our voltage corresponds to our energy, where we have these corresponding cycling curves where we're charging, the kind of total voltage we're putting in is going up, and then we're discharging, getting that energy out, and repeating that process over and over again. We have a few characteristics we see in a curve like this. We have what we call an open circuit voltage. This is thought of as our thermodynamic maximum of the amount of energy we can put in. So when we are charging, we're often putting in more energy, a little bit of excess energy to get the reaction to go. And when we're discharging, we're getting out less energy than the thermodynamic maximum. So that corresponds to an energy efficiency, or in this case, what we call a voltage efficiency. And we can measure the amount of energy we're storing by the capacity. So how long we're applying the current for. So the current multiplied by the time gives us a charge capacity, and the amount of time we're discharging gives us our discharge capacity. So this is just to kind of give you a sense of what the performance metrics we're looking at and how we characterize both the mass, essentially the mass and energy balances of this miniature chemical process. So what we've done with this is apply what I'll call zero-dimensional models. So why we call something zero-dimensional is we're not considering any of the spatial characteristics of the battery. We're only looking at the time-dependent changes in these mass and energy balances to characterize parts of the system. So what that essentially says is we're taking this nice physical picture we actually have of a flow battery and doing what all good chemical engineers do, is we'll take it, we'll kind of squint a little bit, we'll maybe squint a little bit more and say, this kind of just looks like two batch reactors. So we can think of both sides of the cell, if we have a lot of good mixing, as just being two stirred tank reactors where we have our redox reactions taking place. We can then incorporate certain failure modes. So we have our applied current. We can think of how these electrolytes decay. So here I'm showing this generally as some decay process where our charged species goes to some decayed product D, or it can go back to our original uncharged state via a process called self-discharge. And then we also have crossover of our species through the membrane. So again, if our membrane's not perfectly selective, then we might have B crossing over to the A side, A crossing over to the B side. So now we have a much easier to deal with physical picture. And so we can apply some generalized mass balance equations. So I'm going to not go as deep into the math as I'd like to, but just for kind of getting the core ideas of what we look at in this model. Really, this is all built around what I'm calling zero-dimensional cycling. These are just our mass balances. So we're looking at the change in concentration of our species as a function of time. That change is directly proportional to our applied current, scaled by a couple factors. So that gives us our linear change in time that I showed you. And then we're incorporating some additional side reactions in the form of this general R that accounts for crossover and species decay and potentially other side or kind of parasitic processes that we might deal with. We can look at the electrode potentials, our energy balances here. These are just proportional, or a function of our species concentrations. This is given by something called the Nernst equation for those in electrochemistry. And we can incorporate some sort of advective mass transport. So this is accounting for how fast we're pumping and how efficient our mass transport is to our electrode surface. And with all of that information, we can account for the total cell voltage. So this is just the difference between our two electrodes, so the difference in energy between the electrodes, biased by some resistance. So I'm giving this as an ohmic resistance generally, and this is mostly accounted for by the conductivity of the membrane. So we're going to see how that kind of impacts our cell voltage. And we can use all this information to get our performance metrics we care about, so our capacities and our cycling efficiencies, both of these amounting to the energy efficiency. And again, I'm not going into all the nitty-gritty detail here, but what I want to emphasize from this is that all of the performance metrics, everything we get with the performance, the energy, is all predicated on solving our mass balances. So if we can solve the mass balances, everything else falls out. And if you kind of dig into some of these reaction terms, what we can cast this as is a series of first-order reactions across all of our species. And that is a quintessential problem in chemical engineering that we can solve via analytical solutions. But if you were to just generally take this coupled series of mass balances, the first thing you might do is just plug it into something like MATLAB and say, oh, we can just do numerical methods to kind of deal with this at face value. And what you find is that the computation time needed to do that, it's not terrible. It doesn't take too long to run on a laptop. It can range for doing just one charge-discharge cycle anywhere from about 2 minutes down to about 30 seconds. And this was the first thing I did when I was taking a stab at solving some of these equations. I just figured I'd throw it into MATLAB and figure out what I wanted to figure out, right? But I came across this kind of way of looking at it that we could solve this in terms of analytical solutions. And what that does is it drastically cuts down the computation time by a few orders of magnitude. And why that matters is for flow batteries, we're interested in these long duration storage regimes. We want these systems to operate for days, months, years. And so simulating the lifetime of a battery means you have to do a single charge-discharge hundreds to thousands of times. So if you want to do any additional computation on top of this, if you want to do optimization, data fitting, any of that, that becomes pretty intractable pretty fast. And so what this use of analytical solutions unlocks is really a wider range of more versatile analysis looking at the time-dependent performance of these systems. So thinking about making simple performance predictions, estimating parameters from experimental data, those are two things I'm going to talk about here. But we can incorporate general parametric sweeps, look at developing large data sets for things like machine learning, and doing more general optimization, techno-economic life cycle assessments to get a broader sense of how these systems incorporate into a larger energy system. So I'm going to show you some kind of just general data from this, kind of highlight a couple insights as they relate to some other work we've done. So generally, if we apply this model, we get cycling curves that are pretty consistent with what we would expect from a redox flow battery. So a couple things to highlight here is that, again, we're getting these same general curves I showed you on the more general or on the high-level slide. And what we get also generally is that if we go from a low current density to a higher current density, we apply a higher reaction rate, we change those concentrations faster, and we get faster cycling. So we get more cycles per unit time. And each of these cycle above and below our open circuit voltage. So what you can see is that if we're at a pretty low current density, we have a little bit of area above this line, a little bit of area below the line. But as we push the system to go a little faster, we go into we bias the system a little more to push higher currents, higher reaction rates. We get more area above, more area below. That corresponds to a higher or a lower efficiency with which we're using our energy. We're having to put more energy in, and we're getting less energy out. So that's how we kind of characterize that optimization. And our efficiency gets worse with increasing current. So these are just two examples. But like I said, we have kind of general mathematical model that's quick and easy to solve. So it makes it very easy to kind of map out a performance space along a wide range of parameters. So if we, for example, we could make a map of our general performance characteristics, characterizing that current density, which I just talked about, where here we're looking at the voltaic efficiency as a map, going from a voltaic efficiency of 1 down to 0 for a fixed open circuit voltage, and increasing both current and increasing our area-specific resistance. This is effectively that linear resistance I showed you in terms of the energy. So if we have more resistance, we're going to have more energetic losses. And so we can map out this space and say, OK, if I want to achieve a voltaic efficiency of like 80%, which is a pretty good metric to hit, this constrains our space to a set of performance criteria we can access given a fixed open circuit voltage. And if we say vary that open circuit voltage, if we have a lower minimum energy, that really constrains our design space to a much more limited set of resistances and currents. This is pretty typical of what you might see in an aqueous flow battery. But if you transition to non-aqueous electrolytes, which have a larger voltage window, like a lithium-ion battery, this expands our window, but also materials tend to be more constrained in this region. And here we're just looking at 3 variables, but you can imagine the kind of extent we can do with a much larger set of parameters and a much larger design space. And this allows us to really easily map these performance characteristics in what is ultimately maybe a couple minutes to get to something like 8,000 data points in each one of these plots. So allows us a lot more flexibility in making performance predictions. Now, one thing I want to kind of zone in, or focus in on specifically that we use this for was to look at membrane performance. And this is going to talk a little bit to some of the experimental work I've done. So I talked about membranes balancing crossover in the form of capacity fade with their energy efficiency or cycling efficiency. And so the other thing we care about is not just efficiency, but lifetime. So we care about how the capacity, basically our ability to store charge, changes over the course of cycling, going from 0 cycles to 50 cycles. And really, it's this time-dependent characteristic that we really care about when we're using this more computationally fast model. So what happens when we're incorporating crossover here, we start from near some initial theoretical capacity based on the concentration and volume of our electrolytes. And as crossover proceeds, both electrolytes effectively become fully mixed. So where we lower the diffusion driving force until we have essentially the exact same electrolyte on each side. And that plateaus around half of the theoretical capacity, as we're going to lose half of our species when you imagine mixing both electrolytes. So as we slow our diffusion down, we slow down that crossover. So this is characterized by our diffusion coefficient, where we're going lower orders of magnitude. We can see this capacity, what we call a capacity fade, stabilizes. So if we get this crossover rate to be slow enough, then we can get pretty stable cycling over time. So this would correspond to a very selective membrane that would perform well. And we can similarly look at the energy efficiency, where in terms of our penalties on energy efficiency, this diffusion coefficient, once we overcome kind of a minimum low threshold, the energy efficiency becomes pretty high in general. Now, this is at a fixed membrane conductivity. I talked about the conductivity-selectivity trade-offs. If we instead fix the diffusion coefficient and vary the conductivity, here the light purple here on the left is the same data on the right, just to orient you around that. And then if we vary the conductivity, we see similarly, we see changes in the performance. So if we go to a lower conductivity, first off, we're going to incorporate more resistance to our cycling, so a larger energy penalty. This gives us a pretty big hit to our energy efficiency as we go to lower conductivity. But we also see a drop in or an increase in our capacity fade, or just generally a drop in our capacity. And so what that tells us, one, is that the conductivity is hurting us in 2 places. So we're losing energy efficiency, and we're also failing faster. Our capacity is fading faster. And why that is because as we go to lower conductivities, we end up, to push the same amount of current, we need to generate a larger electric field across the membrane. We get a larger voltage drop. And that larger electric field provides a larger driving force for ions, forcing them to cross the membrane faster at the same applied current. So we see all of these trade-offs, and we make maybe a general conclusion that membrane conductivity is more strongly drives our energy efficiency, right? Hurts us along both of the metrics we care about, but I have an asterisk there that, of course, this isn't the only thing that matters. We do need to overcome some minimum threshold of crossover to make that performance work. But definitely, it is a stronger driver of all of our energy efficiency, which is often more a larger performance metric once you overcome that capacity fade. So this was kind of got us thinking more about membrane characteristics, and it got us thinking about back to our general picture of this connection between our material properties and our cycling performance. We have a nice method for predicting those, but it got us thinking about how we are actually characterizing those membranes and what we're doing to actually get those properties in the first place. So to think about this, I want to show kind of how we currently characterize redox flow battery membranes, kind of the general way you might go about characterizing membrane. Typically, you would approach this with something like a swelling and sorption test. Make sure, see how the membrane swells when you put it in electrolyte. Characterize maybe its material properties a little bit. You might then want to know its permeability. So this tells you about diffusion of species. You would put something like an H cell where you have a higher concentration on one side, a lower concentration on the other. And you just watch things diffuse across that membrane and measure the concentration versus time. The slope is proportional to the permeability. So we know diffusivity, and then we want to know conductivity. So you might put something like you might sandwich the membrane between two electrodes, measure something like the resistance or the impedance. And there are a dozen ways to do this. This type of like sandwich cell is just one example. There are a lot of forms of conductivity measurements that all measure slightly different things. But I think we can all agree that none of these really looks like a flow battery. Certainly doesn't look like any of the schematics I've shown you. And the fact that it doesn't look like a flow battery means we're not really getting the characteristics we care about under conditions we care about them. So that is, we're not really measuring the membrane properties when we're applying current, when we're applying electric fields. And as I showed previously, those characteristics matter a lot. So we want to think, OK, so how do we measure or characterize a membrane under electrochemical conditions? There you would look to something like an electrodialysis cell, where you would measure it in situ in a setup that looks kind of like this, where you have multiple receiver electrolytes, you have a donor electrolyte that kind of contains your active species, you can apply a current across this, and you can see how the ions move through the membranes, and then you can measure the concentration of those species. This looks closer to the setup we kind of envision, but it's pretty tedious. We have to measure the concentrations constantly. It's a lot of sampling. It's almost a cell, but we have all these extra chambers. So it's still not quite there. And so what we wanted to ask is if we could more efficiently characterize membranes and in cells and under conditions that more reflect the type of system we're encountering. So what we did is we turned to something we call a symmetric cell. So this is better put as a do-nothing cell, where this is a way we typically characterize stability of our active species, where we cycle the material against itself. So we start at 50% state of charge. So we have equal amounts of A and A+, for instance. And we charge one of these up to 100%, one of these down to 0%, and then we rock back and forth. So we can put it in the species in its unfavored state and see how the capacity fades over time. We design this cell in this way so that we eliminate the impacts of crossover. So why this would be a starting point, a colleague asked if we could use this, and I modeled it, and it showed that it's really good for ignoring the effects of crossover. But we looked at it and said, well, what if we just increase the concentration of one side? So we're still able to rock back and forth from this 50% state of charge. But if we have a higher concentration of this side, we are going to induce some diffusive crossover. And we can still cycle the membrane, or still cycle the cell. Still a do-nothing cell. But if we have species moving over, and this is what we'll call our limiting electrolyte, then as species cross over into that electrolyte, we should see the capacity of that side increase over time. And so we tested this. Again, this is kind of showing the transport phenomena. We're looking at both concentration and potential gradients. And what we should expect to see is that the capacity is going to increase over time. And ideally, that capacity gain should tell us about the crossover rate. So we had this idea of a system. And so we turned to that zero-dimensional modeling framework I developed. and to say, well, let's just see what the model would tell us, and if this would tell us anything about the electric field-driven transport that we see for the species. And so we looked at the kind of changes here. I'm going to go a little bit faster as I'm looking at time. But what we see as we look at the capacity gain, not only is our capacity gain a function of conductivity, so a function of our one of our key transport properties for our membrane, but it also is clearly a function of current density. So we were able, or this effectively shows that change as we increase the strength of the electric field, the rate at which we're moving ions, affects the rate at which that crossover is happening, and we can measure that via the capacity gain of the cell. And it corresponds to both conductivity, and I'm showing this for a fixed permeability or a fixed diffusion coefficient, but it also changes with increasing diffusivity and crossover rate. So theoretically, we said this would work, but of course, we want to show that experimentally, right? So we use here a model chemistry. We use iron 2, iron 3. This is really well-behaved redox species and has very well-defined transport properties. And this is in a hydrochloric acid electrolyte. Our receiver electrolyte is going to have a lower concentration of those species, along with some additional species to balance out the total osmotic pressure, as we can't have a total activity difference, otherwise we'd get osmosis. So we set this up and went ahead and ran it in our lab with Nafion 117, a kind of classical electrochemical membrane. And we see exactly the behavior we would expect from our mathematical models. Of course, I showed you parameters that were similar to what we saw in our experimental techniques. And we see that same behavior. And additionally, because we have a computationally fast mathematical model, we can also use that to easily fit this data very quickly. And if we fit that data, our model fits this performance very well. We can extract out the key transport properties we care about, our diffusivity of both of our species and our conductivity. And that matches pretty well with what we measure ex situ, albeit there are some differences, and some of these differences evolve over time with our performance. I won't go into that. So summarize or wrap up this a little bit. I've only probably a couple minutes to get to my third part of my talk. But just to sum up, analytical models enable a lot of rapid simulation, screening, and higher level performance, like data fitting, that's well positioned to interpret new experimental techniques like we developed in what we called compositionally unbalanced symmetric cell cycling. So that was one part of the equation, and I'll use my last couple minutes here to quickly go over my work on polymer recycling. So as I was pursuing a postdoc, I wanted to take this reactor engineering framework, this work, and kind of apply it to electrochemical manufacturing, starting to think about electrochemical synthesis, organic electrochemistry, and that led me to looking at polymer recycling, doing some really great work in the McNeil group, who's kind of pioneers in this electrochemical polymer recycling space. So we were targeting PVC. PVC is one of the third or fourth highest volume plastics in the world, but it's one of the least recycled, and that's because there are a lot of chemical and mechanical challenges associated with the wide variety of vinyl materials we use. It's in flooring here, it's in soft materials, it's in rigid pipes. So it has a lot of different additives that make it hard to separate and distinguish. And because it has this chlorine, if we try to do anything thermochemical, if we burn it, if we pyrolyze it, we release a lot of gaseous HCl, which is really problematic for reactor equipment. Not to say it can't be done, but it has its challenges and adds a lot of cost. So there's an incentive to look at chemical recycling technologies, thinking about how we can break this down and reuse some of its constituent components. A lot of work in the space looks at specialty polymers, so trying to functionalize that carbon-chlorine bond. But if we're looking at specialty chemicals, that's not going to match the volume of production we get with PVC and vinyl materials. We need to be looking towards commodity chemicals that allow us to scale this process and give us enough of a market demand that might incentivize us to deal with the large volumes of vinyl waste that we have in the world today. So a lot of the work we were doing was looking at making use of the chlorine in this. There are also pathways to commodity plastics, but we were mostly interested in harnessing the chlorine component. And in approaching this from an electrochemical perspective, what's nice about electrochemical systems is we always have to combine an anode reaction and a cathode reaction. So if we consider one of these as a deconstructive reaction where we can generate some reagent here that will cleave parts of our polymer backbone, and then we can use our anodic reaction as a constructive reaction and build that back up into some value-added product. And so the system I eventually settled into was using this framework, breaking down PVC, using methoxide as a reactive base to cleave this carbon-chlorine bond and liberate chloride ions. And then when we have chloride, we can readily oxidize that chloride to chlorine, just as a one-electron oxidation of each of those chloride ions, and get us to commodity-scale chlorine, which has a huge market in the world. And as a tandem, all chlorine today is already made with an electrochemical process. So this is something we know can be scaled, right? So what we ended up doing as an overall process is we built this up, and we decided to separate our polymer deconstruction and our electrochemical steps. So we have what I'm calling chlor-alkoxide electrolysis, where here we're taking methanol and lithium chloride. We electrolyze that. We generate chlorine at the anode, hydrogen at the cathode via hydrogen evolution from methanol, and we generate a lithium methoxide base. Lithium methoxide is a really potent base for PVC reduction at very mild conditions. So we can take that base, feed it into a dechlorination reactor, react that with PVC. We liberate that lithium chloride, methanol, some dechlorinated PVC. And through some materials recovery and separations, definitely oversimplifying the steps in that recovery. But if we can extract out that methanol and lithium chloride, we have a circular process here where one of our only inputs is PVC, and our outputs are hydrogen and chlorine. So this is a direct conversion of PVC to chlorine and hydrogen, both commodity chemicals. So achieving this is a potentially useful pathway for enabling some chemical recycling of PVC. So we get chlorine, we get hydrogen, and then we have some dechlorinated PVC that can either be used to recover energy or can be later functionalized, deconstructed to potentially other useful chemicals. So I think I'm going to have to skip a couple steps for time. This is just breaking down this reaction. We did some kind of fundamental studies in simple lab scale reactors to prove out that this could work. So we established this chlor-alkoxide electrolysis, which hadn't been studied in methanol up to this. So we kind of did some fundamental electrochemistry, established that these reactions could be done in methanol, and established that we could make chlorine at relatively high Faradaic efficiencies. And we get some side products of methanol oxidation, and we can generate our methoxide base also in pretty high Faradaic efficiencies, fairly high yields. So we apply that. The only thing I want to highlight here is that this reaction, again, runs under fairly mild conditions. So kind of the benefit of using an organic base like this is that this is a very potent base. Most alkoxides readily dechlorinate PVC at very mild temperatures. We can do this at room temperature. Heating it up a little bit speeds up the reaction, gets us to higher dechlorination efficiencies. And we get pretty representative structures that tell us we're removing chlorine from the polymer. So we went through materials recovery, had a few steps to precipitate out the lithium chloride and recover it. We applied this to several kind of commercial products. It's in cable, tubing, PVC pipes. It's in a lot of children's toys, so there's like soft, flexible toys. All of these show very high lithium chloride recoveries, and we were able to take that lithium chloride and apply it in our electrolysis system. So that was a little faster than I wanted to go through this topic, but I'm happy to take any questions after. But kind of the big takeaway here is that we were able to develop an electrochemically driven process for generating commodity chemicals from waste PVC. And we're kind of continuing to build, my group is continuing to build on this example to look at more economical and more practical ways of doing this type of chemical manufacturing and chemical recycling. So with all of that, just want to thank kind of everyone that went into this. So everyone here actually contributed directly to some of the work I showed. So I just want to thank my PhD advisor, Fick, my postdoc advisor, Anne. Rahul was my partner in crime in PVC recycling. Jonathan and Adi helped a lot with the mathematical modeling and developing the analytical solutions. Rob and James were both worked on the compositionally unbalanced symmetric cell cycling. Grace was an undergraduate at the University of Michigan who helped us with PVC recycling and is now a PhD student at the University of Toronto. And then I, of course, want to acknowledge both of the groups that contributed to this. I also want to acknowledge my own group now. I can put them on a slide. So we're continuing on some of this great work in electrochemical engineering. Just want to acknowledge all my funding sources, both current and past. And I would be happy to take any questions.
Hey, thank you very much, Dr. Neyhouse, for an interesting talk. So we're a little bit over time.
Yeah, a little tight.
There's nobody in this room after the session, so we've got as much time as you want to spend here, I guess.
Great.
Bertrand,
I got nowhere to be.
questions from the audience? Yeah.
I was just worried that I'm a dangerous chemist. I know not to get into trouble. But on slide 23,
Sure. Oh boy, I'm gonna come over here.
anyway, you showed that H
Yep.
and concentration curve beside it.
Mm-hmm.
Now, I don't know if I'm thinking in terms of diffusion or osmosis, but shouldn't that have a curve that tapers off as the concentration
Yes.
bounces? Thank you.
So yeah, eventually these are going to fully mix, and you would, yeah, as that diffusion or the concentration gradient minimizes, this will eventually plateau. So what this would be showing, and when you would take these measurements, is at the shortest time possible, to where you can capture the behavior without dealing with that change in the driving force. So yeah, if otherwise, yeah, it would take a little bit more modeling to get that right.
Thanks for the talk. Those soft PVC toys for kids, of course, are filled with phthalates. So I'm
Yes.
wondering what's going on with the phthalates there? Are they also getting reduced?
Yeah, so maybe there, almost. I guess I don't really need my slides to answer this, but yeah, so phthalates, what we did when we actually did these experiments, I wish I had my backup slide on this. So what we did with this is we actually extracted out the PVC first. So for that, we separated out the phthalates. We separately we wanted to be able to quantify the lithium chloride yield, and so we need to know exactly how much PVC went in. But if you take phthalates in that, and you react them with lithium methoxide, you're going to get what would be methanolysis. So it would be base mediated, but you would only lose a methanol and not a base. So you would end up with a methyl ester, and that's something we've recovered and quantified.
Is
but
it easier to reduce the ester than the chloride, the alkyl chloride?
it is, but we don't lose the methoxide. So there would be a side reaction going on, but we don't lose any of our base. So it doesn't detrimentally impact the reaction, or at least the reaction of interest. But yeah, we do measure the methyl esters when we do that reaction, but we don't lose any of our, it doesn't mean we need like excess equivalents or anything.
Thank you.
Yeah.
This is really interesting work. I'm just wondering about the broad applicability of this method for other polymers. So PVC makes sense because you're making chlorine, which is useful.
Yep.
But what other polymers can we do this electrolysis on that would result in an equally useful sort of chemical reaction?
Yeah, so I really like polyesters as an example. Kind of going back to the phthalates, you can similarly use the methoxide to do methanolysis of something like PET, something like polylactic acid. Any like PET, for example, would liberate ethylene glycol, which you could oxidize to the aldehyde or carboxylic acid forms. If you want to go even further, you could oxidize those, then do Kolbe electrolysis and make polyethylene. So there are a few alternative routes if you break down fragments of that. And then you also have other halogenated polymers beyond PVC. So with fluorines, it's like polyvinyl dichloride or something where you have like more chloride in here than just the one. So I think there are a range, but it definitely wouldn't be, I don't think it would be applicable at least directly to like hydrocarbon polymers or polyolefins. I think there'd be a more uphill battle.
You can make fluorine gas using it?
Maybe. I can't say that confidently. Fluoride is very hard to oxidize electrochemically. So I would say maybe, but I don't know if you could do that within the stability window of a solvent. Yeah, fluorine's hard to make electrochemically for that reason. Yeah. Oh, one up there?
Just a quick one. You kind of glossed over your yield on
Yes. Well, I glossed over all of it, but
Sorry, what kind of yield do you get?
for the electrochemical yield, so we're up near, here we go. So our overall Faradaic efficiency here is up around 80, anywhere between 70 and 80%. And where this lost current comes from, at least as far as we've studied, is methanol oxidation. So what happens is you oxidize methanol to something like formaldehyde, and that would liberate acid. So that's where we get this H+. Some of that H+, so there's going to be more H+ than what we measure, because some of that H+ is going to cross the membrane and neutralize that methoxide. So that's also why we have a lower methoxide yield. But if you take this H+ and stack it on top of the chlorine, your yields of both of those are about the same. So that tells us that's where our Faradaic efficiency is being lost. And so this is actually another example where our membrane selectivity is hurting us. So if we're more selective to something like lithium than acid, we would presumably have better yields. Yeah, but we were pretty happy with these Faradaic efficiencies given we know what the side reactions are, and it would just be have to put in a little bit of extra current, but we can still get the yields. Back?
Thanks, great. So I think you've answered the question I had. When you were showing the mass balance, I was wondering what was the loss term for the loss mechanism in it, but you just talked about that now.
Yeah.
You also mentioned it being an open system, so I was just curious to know what the loss term might be.
Yeah. The loss term is, you're talking about the R term, that loss term? So that would incorporate, so how we incorporate that into the mass balances is for the decay reactions I talked about, we treat those as first order reactions. So those have just a first order rate constant. Those types of decays are quantifiable. Now, not all decay processes are first order. So that is a bit of an oversimplification, but it covers a lot of observed kinetics. Yeah, so it's packed into that. And then if you take the transport equation, so if you account for the Nernst-Planck equation and make a dilute species assumption, you actually get first order terms that are proportional to some of the membrane properties. So you can quantify those fluxes and turn them into reaction terms.
Okay, thanks very much for the questions. If
Yep.
there are no other questions, please join me again in thanking Dr. Neyhouse.
Yeah.